Hello everyone, I am Avis Nasir. I am a senior software engineer at QC Plus. And today we are going to design Dropbox, Google Drive, such kind of systems where file storage is being required to store the files locally and on cloud, and to properly sync those systems together with each other. Like if you have a local folder present and an online folder present, and without your intervention, you want to properly sync these two systems continuously with each other. So how can we create such a system? Let's deep dive into this. Let's start with the basic title of the system. We can type something like that. So such kind of a system requires a deep knowledge of how the cloud is actually working, how you need to communicate behind the scenes between your cloud and your local systems. Let's start with basic functional requirements here. Functional requirements obviously will be that users can upload the files to the cloud, or you can say to the online storage here, and then properly it will be users can download files from the online storage. There's two are the very obvious, and then the third one is the sharing possibility here. That is the main aspect here in this in such kind of systems, that users can share files with each other which are present on the cloud. Then obviously they both can make changes to those files at the same time, and then our online cloud system will decide that how to properly merge those changes, how to decide that which approach we need to take so that there is not any data loss, but still the changes from multiple users are being shown properly at the cloud. The main thing here is to notice that the systems like Google Docs, Google Sheets Online, that is a separate process that how our system will navigate. We are mostly focusing on the cloud file storage systems and not the actual like system of Google Docs. That is a separate discussion. Users should be able to share files with each other, and then the other will be users local and online systems should be able to sync with each other. That are the two main functional requirements which we will be covering here. And then we will have some non-functional requirements here as well. Like first of all, there will be high availability, or let me put it like this: availability is greater than consistency. And why I am putting it like this is that our system should be 24/7 available. Let me put it back after Azan. Okay, I am putting availability greater than consistency because our system should be highly available 24/7. Any user can should be able to upload, download files any time of the day. And we can compromise a little bit that there is one file present on cloud. One user made some changes onto that file, but there can be a little bit delay. And after that delay, the other user see the updated changes. A little delay, like a few minutes, is compromisable. So that is why availability is greater than consistency. It doesn't make sense that when one user is making some changes to the files, we block the other users, we make them unavailable. That doesn't make sense here. So that is the reason we are prioritizing availability over consistency here. And then obviously the other main aspect here of non-functional requirement will be the size of the files here. We need to properly support very huge sizes. Like in case of Dropbox, normally it is about 50 GB. So users should be able to support large files. 50 GB we can say, because that is in case of Dropbox. I'm not sure about the Google Drive, but we can assume it is like this. Okay, and as I already mentioned, so like we are not considering systems like Google Docs here. So let me put some out of scope things here as well. Like out of scope will be users should be able to edit files online. Obviously, users can do that, but that is the out of scope things. We will not be discussing this feature here. So, and also one others edit files online, view files. Also, users should be able to view files and download them. These features are not only present, but we are not discussing them. That is the main point here, that we are putting this into out of scope feature here. Okay, the complete out of scope items. in case of functional requirements are that they should be able to edit files online, and we are not covering this here. And same goes with view files and download them. Users obviously can view files without downloading them directly on the cloud storage. And same goes with the design of the blob storage systems. We will be using AWS S3 or Azure blob storage system for storing our large binary objects like MP4, MP3, image types, whatever we will be using, text files. But we will not be going directly at how those AWS S3 like systems are being working under the hood. And we have also created our non-functional requirements here. Availability is will be prioritized over consistency. User should be able to support large files. System should be secure and reliable and low latency during syncing operations, upload and download. And in case of outscope, we are also considering some out-of-scope non-functional requirements like scanning of the files to avoid viruses or malware, and file storage per user. And file storage per user is also be out of scope here. And then further, we can also considering versioning of the files. Like one file, we can have multiple versions out of scope from this discussion here. We can move further with some of our core entities. What will be our core entities in this whole system? Uh, we can have three for complete core entities. One will be the file, which will be uploading, downloading to and from the system, and the other is metadata of the file. And third, obviously, is the main entity user, which will be doing these whole actions. We can better to move to some of the APIs, which will be helping us to completely align with our these functional requirements. So first of all, we should be properly interacting with our interviewer that what should be our functional requirements to properly communicate with our interviewer and to align with him is better than to just suppose by ourselves that these will be our functional requirements. And then when our functional requirements are being properly finalized, then these FRs properly help us in designing our APIs. Our core entities, we will be further updating them as we go move further. These are not finalized. Obviously, I have just written down the name of these core entities and not exactly what these core entities, these tables will have. I will also make sure further along when we will be doing the APIs. Then at that time, we can further update our core entities. If our first functional requirement is users can upload the files to the online storage, then to upload, obviously, we will be using the REST API schema here. One thing to note is that actually we will not be using the REST, but to proper understand our system, REST is the most understandable API structure instead of the other ones like GraphQL. So that's why we mostly use REST here. But we will further finalize if we need to replace REST with GraphQL or with the gRPC, whatever. gRPC we mostly use internally during communication within our microservice, but our public APIs are mostly within REST or GraphQL. So, okay, to move further here, users will be able to upload files to the online storage. So to upload files, we can write, it will be a post request to upload files. And to upload files properly, users should be able to provide some of the file. It will be returning, let's say 200 in case. And user will be providing file and file metadata here. And then what we will be using to download our file. To download our file, we will be using get. These are not finalized APIs, but just to complete our functional requirements, this structure will be enough for now. We will be downloading our files. And to properly download our files, we need let's say we need the file ID. For now on, then there can be a feature of bulk download, bulk upload as well. So we can also do that. There is not much difference between bulk upload and bulk download, but just to keep consistency and to focus on the main functional requirements, let me update my out of scope to properly align, and bulk upload and bulk download will be out of scope for now. There's not that much difference, but we need to focus on our main functional requirements for now. File ID, and it will be also returning our, let's say, we will be getting our file and file metadata, and what we will be providing here. File ID we will be providing, and we will be getting back our file and file metadata. And same goes with our share. We can assume that users will be able to share those files with with other users, and for that there should be one another dedicated API to do this part. What we can assume is that it will be another post request to share file, and use in this API will also be getting the file ID, and let's say we'll be getting some status response file, and file metadata will be expected by our API, and then in this way, this API on the backend side will be then sharing this file with the other one. Not exactly file and file ID, but that file metadata will already be present on the backend side. But instead, we will be providing the users array here, and those users array will have the user ID each and or the other users information, and then backend will share that file with those users here. And what other functional requirements we will be having here? Local and online systems should be able to sync with each other, and to properly sync here, one thing we need to mention here that there will be one API which like if we will be using polling on WebSockets, that API will be getting back the status of files which are being changed online. So that will be the get API, which will provide us the changes of some specific file ID. Okay, this changes API will basically be updating the getting the file ID, and after getting the file ID, it will return the changes specific to that file ID. Like it will be returning some change event. Later on, we will discuss that, but will be in this change event. This will be an array. Let's suppose that that will better make sense. That there will be, or we can say that for some specific file ID, this will be only one change event, and there will be one another event API get changes for all. If API file ID will not be provided, then it will return change event for all files. And if the file IDs will be provided, then it will return the change event specific to that file ID. So it can be like this way. That would better make sense. Later on, we will keep on updating these core entities. So until now, if we need to update our core entities, so what can these be our core entities? Obviously, core file will have an ID. File will be saved to some folder. So we can say folder name. File will file will belong to some users here. If we are talking about permissions, so this will be users array, and then there will be size of the file, mean type of the size, like if it is PDF, MP4, whatever, and then like updation time. When was the last time this file was being updated? This will help us. This structure will be the same both on local and on remote, and this will help us in properly getting the updated time of the file and comparing those times and making sure that if we need to sync the local file with the remote file or not, or the vice versa. So this updation time will help in this phase here. One other thing, this file will be present in the AWS S3, so we need that S3 link here as well. S3 link. So until now, this will be the structure of our file. Let's move to our file metadata. It will file metadata. This will be present. Metadata will be present in the database side. So this would be ID, file ID, file ID, and then users will also be present. Users will have ID, and users will have some other permissions, or we can say files, or this can also be array, like user file IDs, all of the files on which this user has permissions, something like that. Let's move to the main structure here, starting from our client. This will be our client, which will be present. It can be any Mac OS client, it can be Windows, it can be Android, it can be iOS, whatever our client will be. In that client, we will have some items present, like first of all, our local internal application will be present here. Internal, if we are considering the app, Dropbox or Google Drive internal app, installed locally along with refresh button. Why I'm typing refresh button here? Because there will be automatic sync mechanism also present here in this app, but there will be refresh button also if the user manually wants to refresh the sync between the remote and the local. So that is why I mentioned the refresh button explicitly here. What other things we will be having here? Instead of this, let me put it in this way, because better to nominate databases in a circle form. Local DB. Let's say we can have SQLite. And then we will be having our local folder that will be, this local folder will be synced with our remote one. And then there will be our security layer here. That security layer will be obviously our API gateway, load balancer. It will also be doing our rate limiting, rate throttling features here. This will be properly navigating our traffic to the some specific nodes which of the service. If we have properly deployed our service to different regions here, it will be doing the SSL termination part as well. So, and then our main service here will be the file service. File service will be doing the main backend compute part here. This, let me make it, I think I have messed it up, the size of it. Okay, now it makes sense. File service will be receiving all of the traffic, and then it will be communicating with our main SWS S3 blob storage, and then S3 blob storage, and then our file metadata will be present here. Here, one thing I need to decide that which database it will be. So my choice obviously will be AWS DynamoDB. One can argue here that it is no SQL database and how it will be able to cope with such traffic. There will be a traffic, and AWS S3 is best suited for such kind of structures. We can use PostgreSQL as well, but AWS DynamoDB is better suited because the data is not that much complicated, and our NoSQL databases also can handle such kind of relations. Okay, we decided with the AWS DynamoDB that it is better suited for such that I am equally involved between PostgreSQL and AWS DynamoDB. There is not much difference here. The relations, we have only three entities present here. And these three entities, file metadata, and users, there is not that much complex relations present between these three entities. And AWS DynamoDB is infrastructure, and all of those headaches will also be handled by AWS. NoSQL, it is very fast. Horizontal, vertical scaling is very much easy as compared to the other databases. So that is the reason that I will choose AWS DynamoDB here. Okay, we created these our file service backend servers, blob storage, and AWS DynamoDB here. Let's start. Our users will start on our first upload file. User will start uploading the file. Uploading file here, and that's this size of the file is very low. It, from the API gateway, it will go to the file service. After the file service, now what options we have? After the file, what we can also do is directly save all of the file in our metadata database. Like if there will be any naive basic engineer that he will choose that to just use any white column database. But it is a very bad approach of directly saving all of the images, videos, each and everything in our database, and don't use any blob storages, which are best practices. This problem is already being solved, but let's assume we will be saving this. What are the downsides we have in this? In this way, we are creating too much complexity on our database. what if the database goes down? Then the horizontal scaling, vertical scaling of our databases will become very much complex. If we are taking snapshots, obviously we need to take snapshots of our database to properly secure our data. Taking those backups, snapshots, horizontal scaling, vertical scaling of our databases become very complex in this way. Like if we are using maybe 100 terabytes of the data there, but storage is obviously taking the most of that part. So that becomes very much complex. So that is the reason normally in this age, these binary large objects like the storage files, MP3, MP4, images, videos, text files, such kind of storage is being stored separately, and the link of those binary large objects is then saved into our metadata databases. It is possible to save them in the databases. Some people think that maybe it is not even possible. It is possible, but it is very much complex and not a best practice here. Okay, we will save our database here, our large object here. Let's save that save file. And after saving file, we will get the link of that. And then after that, we will save file metadata here. That will be our approach here. Okay, this is a good approach here also. But do we have any downside of it as well? It has some downsides. Like just to save the file, how many steps are we taking? We are uploading the file from our browser, let's say, to our API gateway, to the file service. 1, 2, 3, 4 steps. And number of steps is not the issue. The main thing is, and then after a while, what if we need to properly make sure that these two operations are also properly atomic with each other? What if our file gets saved, but metadata was not being saved? Before saving the metadata, somehow our file service got crashed. What will happen in this scenario? Or maybe the other way, uh, maybe metadata was saved, but file was not being saved. That also, the data consistency in either way will not be a good practice. We can save this issue by using a proper two-phase commit here, or the Saga pattern implementation here at the file service level. But still, that is a very complex approach. Instead, what we need to do properly is to use the pre-signed URLs approach. What approach that normally is that instead of saving the files directly from the file service, we need to upload those files using from the client. How does that normally happen? That the other reason for doing that is that normally, like let's say we are storing about 50 GB of the file, as we mentioned in our non-functional requirements. This kind of data, to upload the data, is not feasible to do in this approach. Normally, if we are using our mobile app or browser, those have the limitations of uploading that much file. Browsers limit that. And if the browser is doing that, then our second layer API gateway, like if we are using the AWS Elastic Load Balancer, it has a maximum limit of 10 MB. AWS Elastic Load Balancer will not allow you to upload that much large file, 50 GB. So that is also a limitation. And then goes to our file backend service. Will it allow it? That is also true. So we need to properly use the chunking approach, and we will divide our large file into the chunks, and we will upload those chunks step by step directly from our client to AWS Blob Storage. So that will be the approach here. So how we will be doing that? We will be, instead of getting the file here, we will remove this step. File service will has stored the credentials of this AWS blob storage in its locally, and what it will do, it will create pre-signed pre-signed URL of AWS S3 using AWS credentials cryptographically. So that will be the approach which file service will be doing. It will not be connecting with our blob storage, and it will be saving the metadata here, but then it will be returning the pre-signed URL back. So that's how it will be. It will be returning the pre-signed URL return back. So that's how it will be. And then using that pre-signed URL, our client will be uploading to our blob storage. Okay, in this way, they will be our clients will be uploading to our to our blob storages using the pre-signed URLs. One thing we need to note here that these pre-signed URLs will be authentication added with them. So, and also there will be some expiration date of these pre-signed URLs. So it's not like that anyone with the pre-signed URL and anyone at any time can use this URL to upload to blob storage. It will have some expiration time, like let's say only 5 minutes, 10 minutes, something like that. So okay, that's how it will be upload via pre-signed URL. So clients will use this approach. So I need to also update its arrow now, so that will be only one-sided arrowheads. I think I need to do this way. Client will uploading via pre-signed URL. And now, what about the download one? The download will be, what if the user will be doing this? The user will be doing download file, and the download file service, what it will do, file service will be file, it will be getting the file ID from here. Client will be sending the file ID. It will be file ID will be received here. Download, like let's say it will be like this, file ID, it will be received. File service will get the file metadata from this DynamoDB database, and then in the same way, file service will return back the file metadata. Hmm. That is how it should be. Let's back file metadata, and then using that file metadata, what will client do again? Client will again request our AWS S3 blob storage to download the file. Let me put it that way, to download the file, and the clients will then directly call our AWS S3 blob storage to download the file. We also discussed chunking approach here, that how our clients will be dividing. One thing we need to note here, that chunking part will be done at the client level. And what was our entity here? This file here, we will also be doing the chunks here. File will have a properly chunks present here. Chunks will be an array here, and each chunk will be having its own. Each chunk will be having its own values, like the status of that chunk. That is the most important thing, ID of that chunk, object ID or file ID, that this chunk belongs to this file. What is the status of that chunk? That is a very important thing here, but that is that status being uploaded, not uploaded, uploading. What is the status of the, based on that status, we will be cross-verifying the syncing approach here, status, and I think that are the important things here, or ID, file ID, and the status here. We'll be cross-verifying and using that chunks status. Let me write it down further here. Uploading, uploaded, not uploaded, or you can say pending. These three status of the chunks. What will the client do? Client will divide the whole file into different chunks, and then it will start uploading each chunks to its blob storage using that AWS S3 blob storage. And then when that chunk will be uploaded, then client will update the metadata, its database here, calling the via this path that this chunk is being uploaded. So then on the database, the status of that chunk will be updated from uploading to uploaded. So, and then the other chunk will be uploaded, and then its status will also be updated. So that's how it will be. But there is another downside here as well, that what are the steps we are talking right now? Yeah. Where I should write that steps to upload. I think I can write here steps to upload. What are we writing is client will divide local file into chunks. One thing another we need to mention here, how many chunks? This should be adaptive chunks. What is mean by adaptive chunks here is that based on the network bandwidth, based on the size of the file, we local app should be deciding accordingly that how many chunks should be created. If the network bandwidth is very high, like if we are using 100 MB per second speed, or if we are using 50 MB per second speed network, these two are different network speeds, and there should be a different, like if we are using the same size of the file, size of the file is same 10 GB, but network bandwidth is different. So based on that, chunk size will be larger if we are using the 100 MB per second. But if we are using the 50 MB per second, then chunk size should be smaller. So that's how it will be. Adaptive chunks we will be using. We'll divide file into different chunks, and after dividing the file into different chunks, what it will do, first step will be load chunk to S3. Second step will be to update its status. It's mean update this chunk status in DB. But the better approach than this is that this uh, instead of this client updating our database, better if they can communicate directly with each other. AWS S3 will communicate with our file meta database. So that is a better approach which we will be using here, using S3 notifications. Using S3 notifications, whenever that any chunk will be uploaded, then file service will get its status from S3 blob storage. Okay, so based on this discussion, what is our final approach of that how we'll be doing the verifying the chunks? So first of all, our system will upload to S3, updates this chunk status in database. In, uh, in database. What will further our file service will do? File service before updating status of this chunk in DB, file service will first cross verify its status from S3, and after verification, now service will update its status in DB. And why we are using this approach? This approach is much better than the previous one, where we were just updating the status. There can be situations that our previous step somehow got failed of updating the chunk here. And now there can be a data inconsistency present between our metadata and our S3 blob storage. So it perfectly makes sense for file service to properly check our S3 storage once again before updating its status to in the database. And obviously on the backend side, in our local internal lab, there will be properly logics implemented that whenever our chunks are being uploaded, then to properly show our user properly loading bars, proper statuses that much percentage of chunks are being uploaded, so that user doesn't get bored. It is properly uploaded at all the time, all the statuses. Specifically in case of large files like 50 GB, it probably makes sense to get in touch with user all the time. So we covered all of the steps in case of upload. Now let's move on to the download step. We discussed that in case of download, user will be downloading the file directly from S3 blob storage after getting its metadata from our file service, and then using the AWS S3 blob storage directly. But here we can further optimize this approach to properly, like if the AWS S3 blob storage is present very far away from our region, then due to this, a lot of partitioning can happen. Because if we are present in Asia and our S3 blob storage center is present in Europe, then it probably makes sense to use the nearest data center instead of just directly navigating away to Europe data center to get just one image. To resolve this issue, we should be using our edge location here, like the CDN edge location, which will be present nearest, and our client will first be requesting our CDN, and if the CDN will have our request, our asset, then it will simply return away, and if there will be cache miss, then it will request from the S3 blob storage. It will save that asset into its local for the subsequent requests, and then it will return our request. Then our subsequent request will be fast as compared to the first one. So that's how it will be. We have properly optimized our upload and download, and same goes with the syncing approach here. Our sync will be fastest in this way. Let me write our steps to download. Client will request its nearest CDN, cache miss. CDN will request S3 get back asset and store, and also CDN will return back asset to client. In case of cache hit, CDN will return back asset to client, same like here. So that's how it will be the steps to download. Let's move to our syncing approach here. What will be our syncing approach? There are different APIs present locally on our Windows, Mac OS, Android, iOS, which these APIs locally properly help our internal applications to check if there is any change in our local files, and if there is any change present, then what we will be doing, we will be getting those changes, and our internal app will be properly getting the changes, like as we mentioned here in our this API here, get changes. Our app will be get changes and the changes events here, and how it will be getting the changes from our metadata databases. Our metadata will be properly getting all of the chunks. It will contain the last updated time of all of those chunks, and by getting the last updated time of those chunks, then our internal app will be properly comparing those updated times present locally and present on the remote server. It will properly compare and make sure that if there will be any difference in the updated time, then based on those updated times, our internal app and our file service will sync with each other and update the local file and the remote file. That's how it will be. Okay, let's discuss syncing approach in a much better approach again. What will be the steps which will be involved during the syncing, and how they should be? Syncing is a two-way step. First, it is from local to remote, and then there is a change from remote to local. Let's say that there is some change present locally. Local API we already discussed. It doesn't matter the actual platform, Windows, Mac, Android, iOS, they all have their APIs present. What will be the steps? Our internal app will detect the changes via native API. And then after those changes, let me move on the top left side. Uh, Let me move myself on the top left side. And then internal app will detect the changes via native API. Then what will internal app do? Internal app will push those changes to will first internal app get the will first update metadata DB. Will first update metadata DB. Metadata DB file service here will decide that do I need to create or update these file instances in DB. Create or update its status in metadata DB. If it's not present, then it will create its status here, and otherwise it will update. And same goes with all of the chunks related to this metadata. If it will not only be related to the file metadata, but also related to its chunks here. It will also update its chunks here, as we have already mentioned. Each file where goes here, each file will have its chunks present here as well. What happened to Excalibur sometimes gets crashed. Okay, that's will be the will update its status in DB, and then later on client will upload. The client will sync this file to S3. Actually, internal app will do that. And on S3, how we will be doing that? On S3, we will be using last write wins strategy. As is the strategy we are discussing here. As in case of Google Docs, there are other strategies present which we are not discussing right now. We will just be supposing that whatever the last write on S3 will be, S3 will replace that. And now Let's suppose this is S3 and there is an other client present here as well. Like we have a client 2 present here as well. Client 2 is also has access to that same file here. So what will not exactly it will be connected to this, but let's say it will be actually be connected to our file service here. Actually, it will be connected to the whole system, but let's suppose it is like this. And how we will be doing, mm, we will be managing multiple WebSocket connections here. That is the main point of discussion here, that our system will be managing multiple WebSocket connections to each of our client. Here, we will be managing multiple WebSocket connections. So using that WebSocket connection, like if the one user uploaded one file to S3 now, we will communicate to the other client to get those changes via this WebSocket connection. Via this connection to pull those changes. And one thing we need to discuss here more is that beside this WebSocket connection, we will be using the hybrid approach of WebSocket plus polling as well. The reason behind that is that WebSocket plus polling. The reason behind that is WebSocket connections are a fast approach, but they're not, they're persistent, but sometimes there are chances that those connections get failed at that time. Then if WebSocket connection gets failed, then those clients will not be able to get the latest changes. So to avoid such kind of situations, it is better that beside the WebSocket connections, clients also at sometimes keep on asking the server about the latest changes using that changes API. Where did that go? Changes API here. And here now I am thinking is that there should be a query parameter here as well, since is equal to timestamp. Our local API will be getting the last updated time here. So our local app will be getting last updated time, and then now after that time it need changes. Like our local folder was already being synced at 2:50 p.m. and now it needs to be synced after that. It doesn't needs to be synced since the start. So that doesn't make sense. So to keep such kind of confusions, now timestamp API properly makes sense. So polling after that, so what will our server do? Our server will receive that timestamp, and then our file service will get all of the files from our database where their updated time is greater than our received timestamp. So if any such file is present which is updated after the last sync time, then it will return the metadata of those files into the response of our API, and then our client will get the updated files, those updated files from the S3, and will sync locally. That's how it will be. Now let me just put it right down that server will receive last sync time, get those files which are updated after last sync time. Server, or basically I can say file service, which return metadata of all of those files. Client will then get or you can say download. Okay, client will then get download only those files from S3 and then will sync locally. So that will be the approach of a proper syncing between a local and a remote. If you have any further confusion, that's I have written the syncing approach from remote to local and from local to remote. That's it will be. So if you have any further confusion, please let me know down in the comments. Thank you so much for your time.